It should be ready to roll. So I can't see what you're seeing on the screen. I've got a lot of windows. Howdy. Here we go. We're ready. Roll. So, Gen Chem 1, we've had issues with attendance and getting everything ready and getting ready for this test. And we went over all the stuff that could be on the test last time and things that would be on it. And I realized, man, that's kind of a nightmare. So let's take our time and work some practice problems. So I put together the test. We're looking at 30 questions. There'll be 3 or 4 points each. So what I'm going to do is kind of randomly distribute some of the tougher ones, the longer ones more specifically, some, an extra point possible. All right, so let's start with the number one here. So I've got a practice test. I've also got over here a periodic table. Um, I've also got a calculator, and this is similar periodic table to what we distributed. And you will note I added a row here for fluorine and fluoride on the solubility table. So I'll upload this with the test. Um, if you have any of the data from um, the solubility tables that Dr. Milligan distributed, those work as well. All right, so starting off, I've got 35. Oh, ooh, a word problem. Let's practice doing word problems. So I'm going to make a list of what's given. 35.0 grams of HCl dissolved in water, and I have 150 milliliters. That decimal is important, makes it 366. And it wants, what does it want? Molarity, right? All right, so molarity is moles of solute over liters of solution. All right, so that's not too bad. But I've got mass, so this is my mass. Okay, and I'd like to get it into uh, moles, and I have milliliters. That's going to go to liters. So before I can plug it in, I've got to do some conversions. So I'm going to refer to my periodic table, and I'm going to find that HCl has 1.008 plus 35.45. I can't read it off mine. That's right. And this is grams per mole. And so then I'm going to just set this up with 35.0 gram HCl. I'm going to table format. And so how many grams of HCl? So, no, left-handed. Let the recipe produce extra 1.008 plus 35.45. And I got 36.458. 458. And that's for each 1 mole of HCl. So this will get me moles of HCl. I'm just going to take 35 and divide it by that. 35 divided by, I'm going to use second answer. And I have 0.96 moles. I want everything else off moles of HCl. And then I also need to convert 150 milliliters. Now, the way I teach to do this, 1 milliliter is 10 to the minus 3 liters. And this will be, you could also divide it by 1,000, so 0.15. I'm just moving the decimal place 3 places. 1, 2, 3, 0 liters. So then I come over here and I put 0.96 divided by 0.15. And that will get me close enough for multiple choice, unless sig figs were really an issue. So I'm going to do my previous answer. I'm just going to divide it by 0.5. And I got 6.4 and a whole bunch of zeros. So I'm gonna come over here and I'm gonna put 6.4 capital in moles per liter. Okay, so there's number one done. No problem. So that one we had to use a couple of conversions before we could set it. Number two, it says, what is the molar mass of Ki? So I'm going to come to my periodic table. I'm going to find K. Here's K. That's 39.10. Iodine, weigh 126.9. And this is literally as simple as it's in 126.9 plus 39.2. I got one. Oh wow, exactly 166, huh? Okay. Yeah, it depends on how many secrets you use. Now, don't forget units on this. This is grams per mole for molar mass. Okay, so then let's come over here and scroll down. It says how many moles of Ki are in 225 milliliters. So let's get 220. I don't know how many grams. 225 milliliters. 0.15 molar Ki, and it wants a gram. So it wants this to get met. So I've got milliliters and then this capital M. So remember, capital M, always want to remember that as moles per liter. Right? So when I'm looking at this, I'm going to set this up as conversion. I'm going to take this milliliters to liters. Then I can use this molarity. If I multiply, use that as a conversion factor. So it's 0.15 moles per 1 liter. And then I can go ahead and use my molar mass I figured out previously to get the gram. So my game plan here is I'm going to go from milliliters to liters to moles to grams. All right, so 225 milliliters. 1 milliliter is 10 to the minus 3 liters. 0.15 mole for each 1 liter. And for each 1 mole is 166 grams. Oh, I got to type all this in. So let's see if I can get it from there. 225. I'm going to leave second EE. Negative 3. Remember the 10 is built into that EE. And then I'll need 0.15 and 166. I got the 5.6025 grams. So 5.6 sounds pretty good. Easy enough. So now it's 166 grams per mole. We started actually with a quite small amount of moles. So that one's not too bad. And then in step 4, or question 4, we're kind of changing gears here. So we'll go ahead and get rid of this. So number 4 here says, what is the molar mass of? This is calcium nitrate. So it's C. Pen is trying real hard to dial me here. See if I can poke it just a little bit more. All right, so calcium nitrate. So as I do this, I want the molar mass. The way the book would have you do this, work right when it's middle of the night. So um, the way the book would do it is you make a table and list how many you have of each one. That's okay, but the key to this is to remember this two distributes. We have two of these nitrates. And so it might be easier for you to draw this out is what you have. Each one of these has three oxygens and one nitrogen. And so now you can much easier see what's going on. So when I go and look these up, I'm going to have 40.08 plus 2 times 14.01 plus 6 times, I'm going to round that up to 16. Then we get to type all that in. So 48 plus I got 164.1, which sounds about right. Be 16, we're in 96 and 28, 40. Yeah, not bad. Hang on, let me. Ooh, puppy dogs. Equals for bed or play. Tell me about it now. All right, so then that's it for that problem. Oh, units. So since it said molar mass, grams per mole. Okay, I'm using RTX voice. Hopefully it'll cancel out his barking. We'll find out. We can. All right, 5 is a similar problem. So what is the molar concentration of calcium ion? And oh, I'm sorry, 5. What is the molar concentration of nitrate ion in an aqueous solution of 1 molar, 1.0 molar CaNO2? And this is molar concentration. And here's our key thing. Oh, and don't forget, ions dissociate in water. If it's ionic and insoluble in water, it's going to dissociate in water. So this one, it said it wanted NO3. So for each 1 mole of CaNO3, that's equal to 2 moles of my NO3. And so then I'm just going to take my concentration and I'm going to multiply it by 2. And so 1.0 times 2 gives me 2.0 moles per liter. Or molarity. We keep it as capital M as well. So then number 6 is about the calcium. So the calcium, there's just 1 here. And so it'll be just 1. And we'll keep that as a 1. So that's not okay, 7. What is the name of this? I don't know. I've gotten to where I just read them off. That's the habit you get into. But this CrOH3. All right, now I did my memorization And so I know that this is hydroxide, and it has a -1 charge. Now, CR, when I go look at the periodic table, I've got to find my CR. And here it is. So here's my CO. See that? Nope, you can't see the CO. Or you can't see my cursor on it. Anyway, on the CR, it's right smack in, it's in group 6 or 6B. So it's at number 24. And it is right smack in the transition elements. And so it's not in group 1, it's not group 2, and it's not aluminum. So it can have multiple different charges. This is one we've got to do the math on. And this is the same kind of math that we do when we're doing oxidation numbers later. So it's not too bad. The way we phrase it is the sum of the charges equals the total charge. And that'll come back and help us again later when we do formal charges as well. So here I've got CR. First off, I need to name it. And so that's chromium. All right. So I'm going to name that. Now, I don't have enough information to tell if this is chromic or chromous, so I'm not going to use that system. I'm going to use the stock system. And so I need the charge to go in this parentheses. And so I need to do the math on this. I have 1 chromium there, so I can go ahead and add that understood 1. So I've got 1. I'm going to put an X for its charge. Put an X here, plus I have 3 hydroxides, and each one has a -1. And the key here is the total charge would be up here if it has one. And this particular one does not. And so it's equal to 0. So then x minus 3 equals 0, and x equals +3. So when I go to name this, I'm going to use Roman numerals for that. So chromium parentheses 3 hydroxide. Is it all fit? Yep. And that's my answer. Okay, that's not too bad. Take some practice. Notice I had to go through and figure out what kind of naming system it was. So some things that I looked at when I was in my head is, do I have a metal and a non-metal, or 2 non-metals? 2 non-metals, I'd have to use the covalent naming systems, the prefixes. Then I had to figure out the fact that I had a polyatomic ion. I did that by looking at parentheses helped. I also looked at the fact that it had more than 2 capital letters. And then I had to find which one's positive, which one's negative. Again, the numerization there for hydroxide really helped. And then I had to go through and do figure out that chromium was not in group 1, it's not in group 2, and it's not aluminum. Okay. So let's see, what's the next one here? What is the concentration of a diluted solution made from 30 milliliters of a 0.2 molar stock solution diluted with enough water to make 100 milliliters of the diluted solution? All right, so I immediately see the term dilution. So this is things that were given. And so that equation is on the top of the test in our reference sheet, but M1 V1 equals M2 V2, where this is molarity and volume, molarity and volume. And then I've given 30.0 milliliters, 9.00 milliliters, and 0.200 molar, and 100 milliliters. And I'm going to go ahead and apply a little trick for these equations. And I'm going to look at these and figure out what they, what's going on with them in terms of, this is milliliter, that's a volume. And this is my a molarity, and this is another volume. And so what they want is my other molarity. So what I want to do is to figure out which ones go together. So as I read through this problem, there's 30 milliliters weight with the 0.2. So I'm going to label those 1, give them little subscripts 1, and give these subscripts 2. So that's one set. Here's my other set. I'm not worried about before and after, dilute, concentrated. It doesn't matter. I just want to make sure that I have the right measurements with each other. So I'm going to be solving for V2. So I'm going to go ahead and do that algebra. I'm sorry, M2. This will be my M2. Now, you'll notice that if I solve these volumes in liters, that I could have milliliters and this is milliliters. Basically, if I divide it by 1,000, and then I'd have milliliters, whatever my milliliters are, divided by 1,000, that these thousands cancel out. So these dilution problems, you can save a lot of time by you can do things in milliliters or liters, but not both. In other words, they have to both be in milliliters or both be in liters. You can't have one in milliliters and one in liters. So since they're both in milliliters, I'm ready to just plug them in. So my M1 is 0.2. We stop it. Yep. And V1 is 30. And V2 is 100. So then I'm going to come over here, calculate it back on. And 0.2 times 30 divided by 0.06, and that's moles per liter, so molarity. Now, does that make sense? Let's double check and get a rough idea here. So we had something that was concentrated. We added 30 milliliters, so we diluted it by about a third. So a little bit less than, so we diluted it down. And sure, this 20 to the 6, that's about 30% of that. So yeah, I'll buy that. That makes sense. Okay. Now that's it for 8. Okay, so number 9. Going nice and slow, lots of distractions. So don't worry on the test. You'll have 2 hours. I definitely take 2 hours to even do this. No idea how long we're going so far. 20 minutes. We're rocking along with nice and slow. PBR2, soluble in water. So to do that, I'm going to go over to my solubility table. And I'm going to look on it and I'll see one that says BR is soluble unless it's with. So when I look at this one, I can see. Now can you see that? There we go. All right, so I'm looking through it and I found the BR and it is soluble unless it's with lead that's a +2. So PbBr2, I'm going to double check that. And so this is in group 17. It makes a -1 charge. Now, tet rule, and we'll cover that more extensive later. So PbX and P1, so I put my X. So 1 times X plus 2 times -1. There's no charge out here, so A could equal 2. So this is in fact PB that's up to +2. That's important. That tells me it's insoluble. Don't forget, insoluble means it's going to be a solid. It's the S. Okay. All right, so let's go ahead and check the next one. Oh, it says complete and assign states of matter to the following. Oh, that's going to be some more with these. So we got lots of stuff going on here. Mg NO3 2 plus AF. And I'm going to put my products down here. Now, what I'm going to actually do here, then the first thing is I'm going to go ahead and list the steps out. So, um, one, I need to figure out the reaction type. So there's 5 steps here. Two, then I'm going to get the product parts. 3, I'm going to get the new subscripts. 4, I'll balance it. And finally, in 5, I'll do my solubilities. And that'll help me get the states of matter. Now, in this one, I'm assuming that there's no gases being formed. If there were, that might create us some problems or some liquids. So we're just going to be looking for solids and aqueous on this test. In terms of you predicted it. So I need to recognize that pattern. But this is one thing. So it's with something else. So this is an A and a B. And this has 2 different things. This is a C and a D, the pink showing it. So, okay, all right. And so this needs to go to A, D, and C, B. I'm going to swap the B and the D's. Okay. So now my A piece is magnesium. The D piece is M. The C piece is K, and the B piece is NO3. Notice I brought the 3 because it's part of the piece. The parentheses really kind of help see that. But I didn't bring the 2 because it's got a new partner. So I brought over these parts. Oh, first off, how do you know that? I recognize the pattern up there as a double displacement. And then, so had to do my memorization. AB plus CD goes to AD plus CB. So make sure you learn your types of reactant. All right. So a double displacement then allow me to predict these parts, but I need to also double check my, before I can balance it, I need to get my subscripts. So magnesium is in group 2. It's always a +2. Fluorine is a -1 because it's in group 17. Potassium is in group 1, it'll be a +1. And nitrate, I had to have my memorization part where to know that that's a -1. So that's my polyatomic ions list. And now I'm going to do my crisscross. So this becomes a 1, this becomes a 2, this is a 1, and then this would be in parentheses with a 1. And so that's 1 to 1, and this is 2 to 1. Don't forget you have to reduce the ratio. Okay, so but my ratio is 1 to 2 and 1 to 1, so we're good there. Now I need to balance it, and I'm going to key up on, when I go to balance this, I'm going to key up on my parentheses here. So this, I have 2 nitrates, but only 1 down here. So I'm going to start with that. I'm going to put a 2 here, and that gives me 2 nitrates. That also gives me 2 potassiums. So I'm going to go ahead and put a 2 in front of my potassiums. And that gives me 2 fluorines. Now down here I have 2 fluorines. And I had 1 magnesium, and up here is 1 magnesium. Now I could make my list, but just by following one element at a time, you can do a lot of this in your head. Now I need to check my solubility list. So I'm going to go ahead and look at my solubility list, and here. Okay. So as I look through here, let's see, nitrates, anything with a nitrate soluble, no exceptions. F, now I don't really need to look down here. It says they're soluble unless it's with these, but I could also caught this is with potassium. So with potassium, soluble, no exceptions. I'm going to use that same idea for nitrate and for potassium for KNO3. So MgF, so here's F, and it says it's soluble, except if it's with Mg that's a +2. All Mg are a +2. So this one is insoluble, and everything else is soluble. Now what I'm going to do then is I'm going to label these. If it's soluble, it gets an AQ. KNO3 would get a Q down here. And since this is insoluble, it gets an S. Remove my note. being inside, and it gets an S. And there's that one done. And it says, hey, what type of reaction was it? Okay, this was a double displacement. All right, so we did a double displacement. And then it says, are there any other names? Well, the fact that we made a solid here means this is a precipitation. We took two liquids, added them together, and got a solid. This is also a precipitation. All right. We could also look and see it, decide whether it was um, um, a redox reaction, but none of the charges changed. So there. All right. So let's see here. What's next? Oh, this one's a little bit tougher. It says, which of the following is a strong electrolyte? So this one, I'm going to just look at these pictures. So I have here, this is CH3OH. So this is methanol. And you'll notice they're all still stuck together. They're all one-to-one stuck together. And then just in here, they did not dissociate. It's all covalent compounds. On number two here, I've got H plus and a Cl minus, and that completely dissociates. That's a strong acid, so it completely dissociates. And it splits all in here, and so I got lots of pluses, lots of minuses. So electrons just zip right across it. That's going to be that's my strong electrolyte. But let's go ahead and check over here. We got oxygen, hydrogen, and carbon. And when I look in here, I've got so it doesn't really want to split very well, all right? But it does have a slight positive charge. And so the fact that they've indicated a slight charge here, so this one, no charges shown, lots of charges strong, and a little bit of a charge then will be so this little bit of charge. So this is trying to show us that this is some kind of acid. This will be a weak electrolyte. So this is probably a weak acid. So it's going to be weak electrolyte. So they want which one's strong? It's number two. All right, 13. So this is pretty straightforward. Scroll over here. It says what kind of reaction is this? And so I've got NH3 plus HNO3. And so this initially would look like an AB plus a CD. But notice I only have one product. And so I took these two pieces. And so this is kind of an important lesson about when we're doing these uh, synthesis reactions. It doesn't have to be just the elements adding together. We get two compounds and they come together. The key is only one product. So this is synthesis or combination. What type of reaction is this? All right, so C5H10 plus O2 goes to CO2 plus H2O. So the fact that I have O2 and you get CO2 plus water, that tells me this is combustion. Right? We might see the fact that it's oxidation and reduction, but this one, the main thing is it's combustion. That's what I'll be looking for. What type of reaction is this? And I immediately see something here. There's no plus on this side. So this is a decomposition. I took something complicated and broke it down to its pieces. All right. So even if there were 6 or 7 or 20 pieces, I took something complicated and broke it down to the pieces. So one reactant. All right. So that is a decomposition or an analysis reaction. What type of reaction is this? Now I've got an element by itself, and then I've got something that has two parts. And then, oh, I've swapped this Mg and this H. And so when I swap those, this is a single displacement. Now H is H2 here because it's a diatomic element. All right. This 2 is because it's with magnesium, which has a +2 charge. Okay, so that is a single displacement. We'll also see that that is an oxidation reduction. Okay. 17, a little bit tougher. What is a limiting reactant? And so they give me a whole bunch of stuff here, and then they give me an equation. So let me make sure that I get all of that where we can see it. I'll start right there, and then I can if we need to. So I'm going to make my list here. I've got 2.5 milliliters of 0.5 molar. This up my barium hydroxide, and it says that's OH2. And I've got 30.00 milliliters of 0.1 molar HNO3. And it wants to know which one is the limiting reagent. So limiting reagent, that's the one we run out of. Try to make our yummy, yummy cheeseburgers we run out of. All right. So I can convert one into the other, um, or I can go to moles. And so here's what I'm going to do is I'm going to figure out how many moles I have of each of these. And then I can use my mole to mole ratio given in the balanced equation. So I'm going to double check that it's balanced, eyeballing it. Oxygen's everywhere. There's 6, 8, 6, 8, okay. 4 hydrogens, 2 there and 2 more there, 1 barium, 1 nitrogen. Nope, 2 nitrogen. Yep. Okay. So we'll split this into 2 parts. And I'm gonna go ahead and take it on to my barium nitrate because that's easy enough. And actually, I can see the next question is going to be asking about barium nitrate, and it actually says how many grams are produced. So I'm gonna get ahead on this and read forward of how many grams are in there. So I'm going to take my 2.5 milliliter and I'm going to convert that over. So remember, M is moles per liter. And so I'm going to take the milliliters, and 1 milliliter is 10 to the minus 3 liters. And then 1 liter has 0.5 moles of my BaOH2. And I really should label each one of these as BaOH2, but we're out of space, so I'll cheat a little bit. And so for each, and I'm going to look at my equation, and it says for each 1 mole of barium hydroxide, I can form 1 mole of barium nitrate. Barium nitrate. Now, I could also go on in the next problem. It's going to tell me, hey, we'll stop right there. That's fine. I'm going to go to most. And then I'm going to do a similar kind of thing down here for the nitric acid. So 30 milliliters. Now here it's one. No, wait a minute. I need 2 moles of nitric acid. That 2 is from my equation, my coefficient. I need 2 moles of HNO3 to make 1 mole barium nitrate. All right, so there's my setup. So let's go ahead and type all this stuff in. So type it on, that out. All right, so 2.5, second 18, second 3, and times 0.5. That's it. I got 0.00125 of my product. And on the bottom one, I got 30 3.1. And this one is divided by 2. And I get 0.0015 mole. You can't see my units, they're moles. Now, closer than with my look. So I use 30 milliliters in the one and 2.5 milliliters of the other. So you can't go by concentration, you gotta go by moles. So have to compare these mole to moles. So I couldn't just do it by the amount. I couldn't really tell by the concentration. They were too close. I mean, another half a milliliter, we probably had enough to have excess of that. So the one we run out of, in other words, the one that makes the smallest amount, that's this one. In other words, that's my BaOH2 is my limiting reactant or limiting reagent. Okay. So man, scroll down here. It says, hey, how many grams of barium nitrate can you make in that? Man, barium nitrate. Wait a minute, did we do the molar mass of that earlier? No, not too. Maybe we did it way up early. Well, we'll just do it again. So we're going this amount, and it's BaNO32. So barium is 137.3, 137.3 plus, I've got two nitrogens, 2 times 14.01 plus 6 oxygen. We got 261, and I'm gonna go ahead and multiply that 0.00125, and I got 0.32665 grams. So it's a lot. You get them. Now, another approach you could have done is to use that molar mass here and taken them both to grams. So if I had known ahead of time, I could have done that, no problem, especially if I maybe already had that molar mass. But this is a limiting reagent problem. Don't expect a whole bunch of them, but a little bit long, but not extremely difficult. So the key step here is this mole to mole relationship given in the equation. Now, you can see that we could easily write a problem that had you give you names of the reactants, had you predict then the reaction type and the reaction, uh, the products, and then figure out what's soluble, what's insoluble, maybe ask for the solid that's formed, have you balance that equation, right? Then do tell you how many grams or how many milliliters I started with, and what the concentration was, and have you converted all the way over to grams, or even to number of um, atoms, or even molar concentration of the ions for the soluble one. So, man, we could do a lot with that. So, students a lot of times write that, oh man, there's 30 questions. Dr. J, that's too many. Well, we could write one the question test that had one question. It would incorporate everything in it, but one question. So that's why they don't let me write them stuff like that. The oxidation numbers. Ooh, these are new one. We got a set of rules for our oxidation numbers. So the first one I see here is, so this says, hey, uh, so it says oxidation number of magnesium in magnesium solid. This is the elemental form of magnesium. And so that's going to be a 0. So its charge is 0, so it's also 0. That was easy enough. The N in NO3 negative ion. Uh-oh. NO3 negative. This is nitrate. And it wants the N. So it's the charge it would have if it had a charge. So I'm going to put X there. So 1 times X plus 3 times an oxygen, unless it's a peroxide or it's an element. So if it's a free element, O2, it's 0. If it's peroxide, H2O2, for instance, happens in hydrogen peroxide, then it's a negative 1. But here, it's going to be a negative 2. And then we do have a charge, so I'm going to set that equal to -1. This is why I said don't memorize this as being 0. You got to look for that charge. All right, so x minus 6 equals -1. So x comes out to be 5. So this nitrogen is a +5. This is real important. This is really useful when we look at CO4 and CO2. And why are those so fundamentally different? Is this CO2 here, this is a negative 4, where that's a positive 4. That's a huge shift in doing that. And so it's very difficult to take CO2 back to CH4, right? It takes a lot of energy. Best thing at it right now, still a tree and plants, all right? We're working on it, but so then we've got another one. We've got 21. So 21, it says the copper in this reaction, copper 2 sulfate plus zinc goes to zinc, 2 sulfate plus copper. The Cu in the reactant is being, all right, so they're looking for, I'm going to just focus on that part. PuSO4, and it went to Cu. And they're asking about this Cu. All right, so we can do our math here. Notice I immediately did this when I went to Neiman. It's the same math. So 1 times X plus 1 sulfate, that's 1 of these, and it has a -2 charge. Memorization again. No total charge here. But X equals +2. And then over here, this is elemental form, so it's a 0. So it went from a +2 to a 0. That means it gained electrons. It's that oil rig reduction is gaining. And that's how we should do it. Okay. But Dr. J, man, he's sneaky. He told us 3 definitions. And under reduction, one of them was losing oxygen. And the second one was gaining hydrogen. Doesn't really matter here. So here's my copper. It's with 4 oxygen over here. No oxygens. Oh, man, this polyatomic island is oxygen. These problems nice and easy. So I would say this is reduced because it lost oxygen. Here we can say, hey, it was reduced because it gained electrons. We could also describe this as being -1, -2. We went, well, oh, I'm sorry, the +1, +1 and a +2. All right, so we were at a +2 when we went hang on, sorry, and it was reducing the height. So the oxidation is going up and reduction is going down. Charge or oxidation. All right. What is the formula for lead 4 hydroxide? Pb hydroxide is OH. It's got a -1. Pb, it's telling me that is a 4. So this will be Pb. I need to have parentheses because it takes 4 of them. And this one comes down here, which we usually just leave off. So make sure you have this 4. Make sure you check the ratio of 1 to 4. All right, so don't just put the 4 down here. This in parentheses is telling me I need a dry erase marker that's also a mouse. So yeah, nice. All right, so and magnet. So then it says here, what is the percent oxygen in magnesium dioxide? MgOH. G. And I want the percent oxygen. Right. Yeah, we're gonna have to figure out the mass. And so to get that, I'm gonna get my mass of oxygen divided by the total mass and then times 100. So let's go ahead and find the total mass. Would be 24.31 plus 2 times 16 plus 2 times 1.008. Getting that up on the periodic table. So we'll go ahead and turn on my calculator here. So 4, 3, 1, 32, 2, 1, 0, 8. And I got 58.326. I'm going to go ahead and take 32 divided by that answer, and then multiply that by 100. So even though there's only 2 oxygens here, it still accounts for 54.86% of the mass. So quite a bit. Yeah. Well, she decided she's gonna learn the next chapter. She's gonna be studying ahead. All right. Easy enough. Another balancing. D4H8O2 combustion reaction. 1, 2, 3, 4. One before the birth, one after each plus, one after the arrow. Let's do this long form. Very good. You see how quickly these go. 4, 8, I've got 2. So I'm going to come in, I'm going to put a 4 here, and that gives me 4 of those. It also changes this number. It's now 4 times 2 plus 1 times 1. That makes it 9. I need another 4 up here, and that'll give me 8 hydrogens. And now this math is 4 times 2 plus 4 times 1. That's 12. I need 12 total here, so I need a 6, and that gives me 12. My ratio is 1, 6, 4, 4, and I can't reduce that. So that's nice. All right. Getting down to the nitty gritty here. It says, wait a minute. If hypochlorous acid is, well, this is those chlorates and chlorides and all of this stuff. So this is HClO, and you know what? I like to see these HClO, and then there's an HClO4, and this is HClO3. That's the only one. Now this one is hypo, and it's us, and this is per, and it's it. All right, and so it's chlorine, so it's perchloric acid. And so this is going to just be the it, and this is the us. This is lower than the us. So that's my, oh, sorry. This is the us, and it would be ClO2 in this case. All right, and so us and ick and per ick. So what is the name of HClO3? That's going to be chloric acid. Chloric acid. They don't call it hydrochloric acid because that's going to be HCl. So chloric acid. Okay, what is the name of entry DR4? So now wait a minute, those are non-metal. So I'm gonna come over here, there, click on this N and BR. I don't cross the staircase, and so I'm just gonna use my prefixes. This is di, and that is for tetra. Uh-oh, that's the wrong prefix. Monodichroic. Yep, that's right. That's nice. Okay. And the dinitrogen tetrabromide. Nitrogen. Notice I went in order tetrabromide. Dinitrogen tetrabromide. All right. Next one. What is ClO2? Oh, and it has a negative charge. Now this one's a tough one, right? But the reason for why it's tough, there's a ClO and there's a ClO3 and a ClO4, and they're all negative ones. All right. So this one is my, just like we had before, this is a hypo less than us. And this is us, and this is ick, and this is per ick. And so since it's chlorine, it's chlorine. So ClO2, that's this. It would be for us. Yes. Oh, no, wait a minute. Sorry, sorry. Hmm. The us and the ick, we gotta be careful of. All right. So ick is the 8 and us is the 9. And so this is hypochlorite, and this is chlorite, and this is chlorate, and this is perchlorate. Ooh, almost did I do wrong. So this one then will be chlorate, which is we'll learn in Gen Chem 2 is related over here, the conjugate base of my chlorus acid. Whew, fun. All right. Then it says, what last one? What is the name, the formula of the compound? Magnesium ions react with oxygen ions. So magnesium is a group 2, so it makes a plus 2, and oxygen makes a negative 2. So I crisscross, I get Mg2O2. That's not my answer because that's 2 to 2. My answer is MgO. MG. So there's my answer. Magnesium oxide. OMG. All right, man, that's been plenty long enough. We've almost gone an hour, and it's still shorter than class. All right. Stop it there. My dog's getting anxious. And you guys study hard. I'll post this test probably on Thursday afternoon.